Okay, so now that we've looked at what would happen going along the eigenvectors, and we've talked kind of generally about what would happen if we weren't on an eigenvector, let's take a particular point and we'll find a particular solution for it, and we'll look at what that means on our phase portrait. So we're going to take the particular solution, we're going to find the particular solution for an initial value of 6, 6. So when t equals 0, xy equals 6, 6. Okay, so we'll put that into our general equation. I think we get, it's 1, 2, plus b is negative 1, 1. Okay, so we're going to get 6 equals a minus b, and 6 equals 2a plus b. You can use your linear solver, you can do it algebraically, but what should we find? I think we get that a is 4 and b equals negative 2. Okay, if you need to, take the time, pause the video, convince yourself that those are the values using the linear solver. But we should end up with this as a particular solution for e to the negative t 1, 2, and, oops, not plus, negative 2, minus 2 e to the 5t, and it's negative 1, 1. Okay, so let's see what happens. We're starting off, I'm going to use 6, 2, 4, 6. We're starting off at this point. Okay, not on either of the eigenvectors. We have a particular solution for that. So we're going to put this into our GDC. We're going to put the top line in as one equation, as one function, the x function, and the bottom line as a second function. So I'm going to function, and we're going to have 4 times e to the negative t times 1, because that's the 1 from the top of that eigenvector, minus 2 times e to the 5t times negative 1. Oops, hang on, I put that in the wrong place. Times negative 1. Okay, so this is a function for x based on t. So the x values in the calculator are actually our time values, and it's going to give us how the x is changing over time. I'm going to put in the bottom part of the equation. This is going to tell us how y is changing. Times 2 minus 2 times e to the 5t times 1. I'm not going to bother writing the times 1. 4 e to the negative x times 2 minus 2 e to the 5t. Okay, that all looks right to me. Okay, so let's take a look at the table. We are going to go for what happens as we're going in increments of 0.1 for time. So this first column is time. You can see at time 0, function 1 is x and function 2 is y. We've got the point 6, 6. So let's look at as time increases positively. You can see the x values are increasing quite rapidly. The y values are decreasing and becoming large negative y values very quickly. If we wanted, we could plot some of these points. So I'm going to plot the next point as roughly 7, 4. That's where it's going to move to. So 7 and 4 is over here. I'm not sure I'm going to be able to plot many of these points. Maybe if we zoom in again. Okay, that gives us a little bit more detail, doesn't it? So I got to roughly 7, 4. 8, 2 is the rough point I'm going to take. I'm not going to be able to do this particularly accurately, but it's going to end up around about there, and then I'm losing it off the side of my graph. So that's where we're heading. And then let's look at what happens when we kind of work backwards in time a little bit. So what about when x is 5.5? Oh no, it doesn't actually reach 5.5. So it goes down to about 5.6 at around about 8.6. So 5.6, and that is up here. So it's going to go roughly there. And then what happens after that? As we go further back in time, you can see both values are increasing. Okay, and you can see that the y values are roughly twice the x values, which is kind of what we'd expect along that eigenvector. Okay, so it's going this way over time. And yeah, clearly, if we had a larger graph, we could fill it in. Going up in smaller intervals of time would give us more detail as well. But it's coming from a point where the y values are twice the x value, which is that eigenvector heading into the origin, and it's heading to two points where, let's look, the x value and the y value should be opposites, and you can see, yep, they're roughly opposites already. So it didn't take long, just over a second, or whatever we're measuring t in, and we're pretty much going along that route with the eigenvectors. Okay, you can do this with many points. You could like find a couple of points in each of the sections that we've got. Well, actually, the purple line was a bit of a just one we were using to estimate it. But you can choose a starting point. You can come up with a particular solution like we did in part C for a new starting point. You can put it into your calculator. You'll just find you have to adjust the A and B values, so that shouldn't be as much work to put into your calculator. And you can plot roughly where they are. And you could do that for all the different regions. You might want to pause the video and have a go at doing that now.